Hi, this is Lab 2 covering the motion of a falling object. The objectives of this lab were to observe the motion of an object that is dropped from rest and falls straight down, to construct a computational model that includes only the effect of gravity, to construct a computational model that includes both the effect of gravity and the effect of drag, and to compare the computational models made in VPython with the experimental model. In this lab, we are able to use Newton's second law. Force equals mass times acceleration, and in this case, the acceleration is due to the Earth's gravitational pull and is equal to 9.8 meters per second squared. The net force is not equal to 0 because the object is accelerating, and when drag is taken into account, the net force is equal to the object's weight plus the drag force. Once again, the final velocity is not equal to the initial velocity because the object is accelerating. Using Tracker, I analyzed the motion of a falling tennis ball. I set my axes so the object was moving in the negative y direction. From this, I was able to extract position versus time data that can later be compared to the data from the computational models. Some important codes used for the computational model included equations for the gravitational force, or the object's weight, the drag force, and the net force. Here's the code that was used to create a computational model without a drag force. What makes the drag force 0 here is the fact that b is equal to 0. The equation for drag force here is negative b times the velocity squared. Further down in the code, adjustments were made so that when the program runs, a clear visual appears. There's an arrow representing the gravitational force in the negative y direction, and an arrow representing the drag force in the positive y direction, if one is present. The arrow scale was determined by dividing 2 by the weight of the ball, remembering that weight is 9.8 meters per second squared times the object's mass. When running this program, it is clear there's a gravitational force acting on the ball, but no drag force opposing it since there's no upward arrow. Since there is no drag force, the computational model predicts a larger distance to be traveled than the actual distance covered in the experimental model. In order to try to better represent the experimental model, a b value must be added. This was done by trial and error until the predicted distance covered matched the actual distance covered. When running the program, it is evident that there is a drag force on the ball that acts against the gravitational force because there is a small arrow pointing upward. After graphing the three models, it is clear that the computational model with drag force best represents the experimental model. The computational model without a drag force overpredicted the distance the ball would cover because there was no force opposing the gravitational force. After creating a velocity versus time graph, it is clear that none of these models predicts a terminal velocity, since none of the lines are horizontal. However, they all have constant acceleration since they are straight downward sloping lines. Also, the ball would have a different terminal velocity if it was thrown down instead of starting from rest. Instead of starting the lines at the origin, the lines would begin further down on the y-axis. Once again, the acceleration would be constant. From this lab, we saw that an object in freefall has a gravitational force and drag force acting upon it. These forces cause the object to accelerate towards Earth. In this lab, the final velocity does not equal the initial velocity since the object does not move with constant velocity. If the drag force had the same magnitude as the gravitational force, the object would move with constant velocity. However, the drag force is smaller than the gravitational force, making it accelerate. Thank you for listening to my Lab 2.